at this interesting topic, differential calculus. And under this, we want to see briefly the meaning of differential coefficient of a function. So, differential coefficient of a function. So, let's look at the definition of differential coefficient. From here, differential coefficient of a function is also referred to as the derivative. So we can call it derivative of a function, derivative, or we can call it the rate of change of one variable with respect to another, etc. Now, given a curve C in the Cartesian plane, whereby we have this as the y-axis and this as the x-axis. So here we have the curve C here, and we have 2 points on this curve, and let this be point P, which is x, comma y, and we have another point Q, and Q here is above this point P. So x here, there is a little increment in x, so that's x plus delta x. Delta x here means little increment in x, then comma also little increment in y, so we have y plus delta y. Then the line joining P and Q, we have it here, and this line is line PQ. That is, here we can get the slope of this line. The slope of this line from here is given as this. That is, we have change in y here, delta y, and this is change in x over delta x. So that means the slope of the line PQ, slope of this PQ, let's denote that as m1, and which is equals to delta y over delta x. So that is the slope of this line PQ. Now, the differential coefficient we are interested in is related to tangent at this point P. So we have the tangent, we have a tangent. A tangent is a line that touches this point at this curve. So let's say this is tangent T. Now, the slope of this tangent is what is referred to as the differential coefficient. And how do we get the slope of that tangent? Let's say the slope of the tangent is m2. Then this will be equals to, now we can get that from this PQ, as this delta x here is tending to 0. That is, here this line PQ will coincide with this tangent. When this delta x is reducing and it's coming down to become 0, this line which is PQ will tend to lie with this line which is tangent, which implies that the slope of this tangent m2 will be the limit as delta x tends to 0 of m1. So that is the slope of the tangent, which is m2. So the slope of this tangent is the limit as delta x tends to 0 of m1. That means we have m2 equals to limit as delta x tends to 0 of m1 here is delta y over delta x. So what we have here is therefore referred to as the differential coefficient of a function. That is the limit as delta x tends to 0 of delta y over delta x. And we also write this as dy dx. So differential coefficient of a function. Therefore, properly defined, we can say differential coefficient of a function denoted as dy dx is now equals to limit as delta x tends to 0 of delta y over delta x. So here we have the definition for differential coefficient, which is also referred to as derivative of a function, or the rate of change of one variable with respect to another variable. So that is, differential coefficient of a function. And from here, let's derive the first principle formula of differential coefficient. The first principle formula from here, given that we have a function y equals to f of x, then we have a function, say we have a function y equals to f of x. Then we had a little increment to y and x from here, that is on the left hand side, a little increment in y, that's y plus delta y. Then at the right here, we have f of x plus delta x here. So we have added the little increment to y and x. Then next step here, don't forget what we want to derive here is the differential coefficient from the first principle, and from the formula of differential coefficient, we already know what we have, that is the limit as delta x tends to 0 of delta y over delta x. So this is what we want to derive from the first principle. That means here, what will be on this side should be what we have here. Then that means I take y to that side, and I have delta y left here, which is now equals to here becomes f of x plus delta x, then minus y from here. That is, instead of writing y, since y equals to f of x, I can write f of x instead of that, and we have delta y now equals to f of x plus delta x, then minus f of x from here, since y equals to f of x. Then, now from here, we need to divide both sides by delta x, because what I have here is having divide by delta x. So divide through by delta x here. Then here becomes delta y over delta x, then equals to f of x plus delta x minus f of x, then over delta x from here. So we divide through by delta x here. Then what left is to introduce the limit as delta x tends to 0 on both sides. Then this side will now be limit as the delta x tends to 0 of delta y over delta x will then be equals to, also on this side we have limit as delta x tends to 0 of f of x plus delta x minus f of x, then over delta x. So which implies that here we already have the differential coefficient of a function on this side. So this is also known as dy dx, and which is equals to now limit as delta x tends to 0 of f of x plus delta x minus f of x, then over delta x. So here, this formula here is the formula from the first principle. That's first principle formula to find the derivative of a function. Then We can apply this and see how this is used to differentiate a particular function. Now, example, differentiate this or find the differential coefficient of this function y equals to x squared from the first principle. So find the differential coefficient, of y equals to x squared from the first principle. Now, from here, solution from what we have. Now, the function given is y equals to x squared. That's in form of y equals to f of x. So, which implies that here, f of x we have here, when we compare this with y equals to f of x, the f of x here now is x squared. Now, when we recall from the first principle formula, that is the y dx that we are finding is equals to the limit as delta x tends to 0 of f of x plus delta x minus f of x then over delta x. So this is the formula we are using. Then now that means we need to get f of x plus delta x. So that means here f of x plus delta x will then be equals to, that give us, we need to add delta x to this function. That means we have x plus delta x squared. So that is f of x plus delta x from here. Then that means the y dx becomes here limit as delta x tends to 0 of f of x plus delta x, which is now x plus delta x squared, then minus f of x, which is x squared, then over delta x. That is here now, we simplify here, and this gives us limit as delta x tends to 0. Expansion of this bracket give us x squared plus 2x delta x plus delta x squared. That's the expansion here. Then we have minus x squared here, which is divided by delta x. Then, when we simplify further, it implies x squared minus x squared. This can cancel each other. Then we are left with limit as delta x tends to 0 of 2x delta x plus delta x squared, then over delta x. Now, this fraction we have here, we can separate this fraction into two fractions. That is, here, this is same thing as limit as delta x tends to 0 of 2x delta x over delta x, that is, and plus delta x squared over delta x. Now here we can reduce this because here delta x, we cancel delta x here. That means we have 2x here, and also delta x cancel one delta x here, remain delta x. So what we have now means we have the y dx now will now be equals to the limit as delta x tends to 0 of 2x plus delta x. Now, since delta x is tending to 0 here, that means anywhere delta x appear, we'll put 0 from there. So therefore, the y dx here now, okay, let me clean this, excuse me. So that then it implies that we have the y dx will then be equals to 2x plus 0 from there. And finally, the y dx is now equals to 2x. So that is the derivative of the function given from the first principle, which I believe you have gained one or two things in this class. And thank you for joining us. Now let's look at this against the, next class. You can as well try this and differentiate from the first principle, given that y equals to 1 over x. So this is the first one. And the second one, y equals to x raised to power 3. So differentiate these two from the first principle against the first, class. Thank you for joining. This is Master Teamwork Class once again. Thank you for joining us. Don't forget to subscribe for more of our videos, and see you next class. Bye for now.